I hope everyone can hear me. Let me clarify with our, okay. Just some announcement before we started our lesson. The first thing is, I think everyone got the news. We are actually changing it to 12 weeks at semester. That means we have to cancel everything on week 13, including lectures and tutorial. But because we actually just scheduled the 12 week 13 tutorial to be consultation section with our projects, so it's okay. Don't have as much. But actually, if week 13 is cancelled, today will be our last lecture. So I actually claim all the stuff today. Try to deliver it all by today. Okay. So today, originally, we planned to have only surface reconstruction, which is quite a technical and heavy subject. But we add in the last week, week 13's topic, which is procedural modeling, and the other one is surface modeling on this topic. Okay, so I hope if a bit longer. So if you cannot survive for the whole lecture, please go and read later or watch the video later. So let's get started. Before that, let's get some preparing. Oh. Okay. Oh, one more thing is about the exam. For the exam, you also know that we all convert to the e-exam. So we'll plan the exam to be on the same time slot as the original planned, but they will be online. So what we'll do is we'll do an e-exam. So it's a Zoom exam. So later on we'll talk about more of that. But the good thing is, if you need to go back to your country, you actually can do your exam in your country. Okay, let's say you don't want to go away, you want to actually take the exam in other than Singapore. That's all possible. I think that solves a lot of problem. Okay, any questions before we go on? If no, then let's start. Surface reconstruction. This is one of the things when we acquire data from real objects. Okay, we actually can obtain shapes from a lot of different sources. I think one of the major sources is point clouds. That means you use a scanner, then you actually use laser or sound, or actually you sample a lot of points on the surface. The other one usually people do is Watson densities, which you can do it with MRI or those scanning device. But we'll focus on these two and talk about how to reconstruct surface. Okay. First, point clouds. That means I'm given a point, I want to find triangles. Think about that. We actually play this in our childhood. I hope in before that we actually connecting dot. So you're given the dot, but you want to connect it. Most of the time we actually do have numbers, but if you don't have numbers, how do you connect it? I think for humans, usually try to match a shape in which you see the dot. Oh, actually it looks like a fork. Then actually I connect it. But for computer, if you don't use AI, it's kind of difficult to connect a dot. If you just only depending on some geometric structure. The big question is which dot to connect to which dot. Okay. So historically, without AI, researchers tried to estimate the local nature of the point set. For example, I find a near local neighborhood, a small group of them, a small group of points. I try to see what does it look like. Usually for an object, the local neighborhood will be like a surface. And we try to compute some values, for example, approximate a tangent plane, detect the normals, or use a minimum span tree to actually try to find some local neighborhood and try to connect them. And but today we mainly focus on something called the Voronoi and Delaunay approach. And I will introduce, actually these two concepts we talk about for some time is actually available or applicable to any dimension. But however, it will illustrate all in R2, which means 2 dimension first. Okay. Let's see. Let's say this is a Singapore map, right? For example, let's assume Singapore only have 2 fire stations. One is in Tuas, one is in Changi Airport. My question is, if there is a fire somewhere, you want to call the fire station which is closer to you. For example, if you have fire here, I think it's Choa Chu Kang something, right? The most near one should be, you should call the Tuas. You don't want to call the Changi Airport one and then you go all the way, right? So if you have a fire here, this fire will actually, I would rather call the Changi one to come, or rather than I wait for all the Tuas fire engine to come, which will take longer time. So the question is, for all the spot in Singapore, how do you determine which fire station to call if you have a fire? I include every point. The answer is, you can actually find a perpendicular bisector between these two fire stations. That means I draw a broken line that is the straight line between these two fire stations, and I actually draw a perpendicular bisector which is perpendicular to this, and both of them have the same length. That's called perpendicular bisector. And by this red line, I actually can say anything on the left, I should call the Tuas one, and anything on the right, I call the Changi one. That's how actually for this diagram, you actually can think of, I actually divide the space into left part and the right part. And all the left part need to call this fire station, and all the right part will call this. How about if now we have more money? I have a third fire station. How should I divide the land such that it observes the same rule of those within the area that will be closest to that fire station? So you should divide. So for example, this fire over here, which you will call, of course, you could still call the Tuas. This one now originally was calling the Changi one, if it's only 2 fire stations, but now because you have a fire station in Woodland, that's why you call the Woodland ones. How do we divide the land? And if you want to divide the land, you want to divide in this way. Okay, you can somehow see that this one is the perpendicular bisector between these two. This one is the perpendicular bisector between these two, and this one, of course, was the perpendicular bisector of these two. So how do we construct this diagram? But what you see here is this Y-shaped red lines actually divide the space into 3 regions. And this region is actually called the Voronoi diagram, in which is the same concept people think about that before. It's actually very, very old. You can see it's like 500 years history of time. It's by Descartes. He was thinking about the universe, in which our problem is a 2D problem. He was thinking a 3D problem. Why? Think about that. In universe, if you talk about gravity, let's say this is a planet Earth, this is another star, and this is a star. Each of star will actually have gravitational force to enforce so-called affecting objects around it. For example, if I have some object here, let's say I have a rocket here. If the rocket has no rocket, okay. So if the rocket has nothing, no force or not moving, the rocket will be attracted to this planet. But if the rocket is more close to here, then it should be attracted by this planet. So the question is, how do you divide the space in 3D such that you know that in which region will attracted to which planet? So that's what Descartes think about. So for Voronoi diagram, you have a finite set of points in which they're called sites, as in all these points here. For example, this one, this point, this point, this point, this point, this point. So these are the points I'm talking about in here. And we assume this general position assumption that no 2 plus d points are co-spherical. That this one you just leave it in mind. So for example, in R2, we don't have 4 points co-circular, okay? Because in R2, every 3 points will be co-circular. But let's assume this first. We will use this general position assumption first. So if it's like that, I can define the distance measure from one point. So for any point in the space X, this is a distance between that point Pi, and each point Pi is one point set in this point set. And for every 2 points, the perpendicular bisector of ij should be all the points X in the space such that they have the same distance from I and point J. Okay, so these are all the perpendicular bisector of ij. So for example, if I have 2 points here, this is the Lij, in which you see that Lij is actually equal to Lji, because the perpendicular bisector of ij is equal to the perpendicular bisector of ji. And we define the half space such that Hij means those point is closer to I than j. So if you see back the diagram, this yellow area is Hij, because all these points in the yellow area is actually closer to point I than closer to point j. And the other one is Xji over here. Okay, with this, the vonoid region of a certain point Pi with respect to the set S is, I take every other point in S. I want to find the intersection of all Hij. That means I want to find the region that the distance to I is smaller than all the distance to J, which simply means the vonoid region, this symbol actually we use new, this is new, okay, that contains all the points that has a shortest distance to Pi. Okay, let's try an example. For example, I want to find the vonoid region of the point P1. P1 is here, okay? I want to find the vonoid region of them. Then I use the Hi. So for example, between P1 and P2, you have 2 half space. One is H12, which is this green area is all the points that is more closer to P1 than P2. And the white one, of course, is the other way around. And this one is H13, which means this gray area is all the points that's more closer than 1 than 3. And you repeat this for every point. For example, then you have this is H14, and you have H15. And all this colored area, each of them is the point set that is closer to P1 than the other point. And if you want to find the area that is closest to P1 than all the other points, that is the intersection of this half space, which is this region. And this region is, we call it the vonoid cell of P1, which call it nu 1. Nu is a symbol nu 1. And if you construct the same vonoid region for every other diagram, then you should have this. So you can see P2, nu 2 is here, and P3, V3 is here, and so on. So each of the region is the region that is closest to that P1, P2, P3, or P4, or P5. This is called the vonoid diagram. You can see some definition of vonoid diagram. First, every point set has a non-empty vonoid diagram, which means every point will have its own area that is closest to him. And every vonoid diagram is convex. You can try to prove it. Why is every vulnerable region should be convex? Why cannot I have a star shape or moon shape for the vulnerable region? And the vulnerable region is unbound if P1 is on the boundary of the convex hull. Unbound means, for example, you see that P3 is bounded, but all the P1, P2, P5, and P4 are unbounded. They actually go to infinity. And the intersection of the interior of V1 and V2 is empty. Interior means I only intersect on the exterior edge, which is this one, okay? For example, this two is intersecting here. There's no interior intersection with volume. And if you union all the vulnerable cell, it should be equal to the whole space. That makes sense, right? Because every point will be closest to one point. So, okay, now let's see what is in the nature. With actually, nature have a lot of vulnerable cells. If you think about that, bubbles create vulnerable cells. These small bubbles. Some veins on the leaves, even some animal patterns or bone structure, they all exercise some vulnerable cell structure, in which you can think of that in nature actually a lot. Even wings of dragonflies, okay? So a lot of them actually do vulnerable cell structure. And we actually will have a dual structure called Delaunay triangulation. What does that do is, whenever two vulnerable cells meet, you put a simplex there. I hope you remember what is a simplex. A simplex can be a point, can be a line, one line segment, or can be a triangle. So let's see. First, because one vulnerable cell intersect itself, so we actually put in all the vertex. And then you can see that two vulnerable cells intersect each other. P1 and P2, they are intersecting at V12. New 12 means this edge. So the vulnerable cell of P1 and the vulnerable cell of P2 actually intersect on this edge, which is a non-empty intersection. If they're non-empty, then I actually add the straight line with P2 and 3, P1 and 2. So you can see which of the other line that have a straight line. For example, P2 and 3, I actually have a straight line. Let me draw a straight line. P2 and 3 has a straight line. P1 and 3 have a straight line. P1 and 5 have a straight line. And P1, 3. So these are all the straight line I want to put on the right diagram, okay? Currently, you only have point and lines, but you also can see that here. This point is the intersection of three vulnerable regions. Vulnerable region V1, V2, and V3. That is called V123, which is this point. If these three vulnerable regions intersect on a point, what we'll do is we actually will add one triangle. Let me clear the drawings. You add one triangle like this. Okay, this yellow is a triangle of P1, 2, and 3. And if you fill in the whole picture, you will have this. Okay, so all together you have 5 points, 8 edges, and 4 triangles. And you can see that this is not for everything. For example, you do not have an edge P15. Why? Because the vulnerable region of P1 is here. This is the vulnerable region of P1. The vulnerable region of P5 is over here. And you can see this vulnerable region does not intersect each other. And that's why I do not have an edge of P15. In the same time, you do not have a triangle P142. I don't have a triangle P142. I don't have this triangle. Why? Because these three vulnerable regions do not have one common intersection. And this one is called the Delaunay triangulation. if we assume general position assumption, the DeLonghi triangulation is the convex sum of all the point S, and the DeLonghi triangulation should be a simplicial complex. And this DeLonghi triangulation and Voronoi complex are actually due to each other. That means if you look back on this, a point in the DeLonghi triangulation is a region in the Voronoi cell. And then a line in the DeLonghi triangulation is a line in Voronoi cell. And a triangle in the DeLonghi triangulation is a point in the Voronoi cell. So they're due to each other. So that's how we construct a 2D DeLonghi triangulation. And actually, we can extend all this into 3D. The only thing different is when you do this construction here, go back to here, this Lij, when I define in a two-dimensional space, this is a line. Because between 2 points, the point set that have a common distance between these two is one single straight line. But think about it, what will it looks like in 3D? If I have two space points, let's say, what is the dividing objects that divide from the Earth to the Sun? Then it's actually a plane. And this plane will divide the space into two half space, 2h. So in 3D, you can apply this totally the same thing, such that for 2 points in 3D, the line of common distance will become a plane of common distance. And then it will divide the space in two half space, and the Voronoi region will be a convex polytopes. So after you get a few half space and they intersect each other, there will be a convex polytope for each of the points. And in general position assumption, only at most 4 Voronoi regions will be meeting a point, and that will create a tetrahedron in the DeLonghi triangulation complex. So for example, these 3 Voronoi regions intersect with each other, and you can see that they are actually intersecting with an edge here. This one. So these 3 Voronoi regions actually intersect this edge, and this edge will form a triangle in the DeLonghi triangulation. And you can have 4, and they actually make a tetrahedron. So just a comparison between 2D and 3D. 2D half space actually bounded by lines, and the Voronoi cell of each point is actually a polygon. And 3D is the Voronoi cell of each point is actually a polytope. And a line in DeLonghi triangulation is if the 2 Voronoi cells share an edge. And a line in DeLonghi triangulation if 2 Voronoi cells share a face. So because the 2 Voronoi cell is actually a polytope, so 2 polytopes can actually touch each other on the face. But if 3 Voronoi cells touch each other, they actually share an edge, and the DeLonghi triangulation will be triangles. Okay, so for example, let's say so first, the intersection of all the half space will make each point having a polytope as its Voronoi cell. And a line in the DeLonghi triangulation is actually this one. I'm talking about this one. Let's see. This is the face of when 2 Voronoi cells touch, and this Voronoi cell and this Voronoi touch such that it will make a DeLonghi edge here. And if 3 of the Voronoi cell touching, which we just talked about, that in the last slide. This is the 3 of the Voronoi cell touching, and that's why they will actually create a triangle in the DeLonghi triangulation. This one. Yep. Okay. And if you construct the whole thing, it will be a 3D simplicial complex. And you can see all these polytopes will actually construct a triangulation or tetrahedralization in the 3D space with the points. So go back to our surface reconstruction. How do we use it? But let's try to use a 2D example such that it's more easy to see. Let's say these are the point set, right? You can see this point set somehow resemble a shape. But how do I know which point to connect to which one? For example, for this point set, very intuitively, you will think, oh, this connect to this connect to this connect to this connect to this, and you actually connect all this with a straight line to connect a shape. But how do the computer know that this point is not connected to this one? And then connect, and this one connect to this one, and this connect. How do the computer know it's not connected like that? Let's see some observation inside a small area. Let's zoom in this yellow area. See, for example, this Voronoi cell, which this is the Voronoi cell of this point over here. And this point actually has a lot of freedom of connection. This point can connect to, this is the sharing between the neighborhood. I can connect this point to this one. Also, this is sharing this one, so I can connect to this one. Also share and you connect to this one. And this one over here, I also can connect to this one. So this point actually have 4 neighborhood I can actually connect to. However, if you see by your human judgment, you think you should actually connect these 2 edges, right? Do you have any intuition why should I connect these 2 edges instead of the 2 broken lines? One of the intuition you can see that these 2 broken lines refer to these 2 blue lines, right? Do you see there's a difference between these 2 blue lines and the 2 broken lines? The 2 blue lines are actually longer in this cell. So you can see that if it's a surface point, somehow you can actually see it also for the other, for example, this one, and let's say this one. You can see they have some very long side. For example, this one is another long side. This is another long side here, another long side here. So you can see the shape of the Voronoi cell. For example, this one. If you sample some point dense enough, it all looks like a tube. And what you want to connect is those points that share the face that is longer or larger. So in 3D, it's the same thing. And this point P, if you sample all the surface point dense enough, the point P will actually is like a crystal, like a long crystal like that. And what you want to do is you actually want to connect to the point that is beside the crystals instead of connecting a point that is vertically. So this is the basic algorithm for surface reconstruction without knowing the surface, in which your Voronoi cell should be able to tell you. And this algorithm is actually called Cocoon algorithm. It's not Cocoon, it's a bit like Cocoon, but it's called Cocoon algorithm. That is one of the very popular surface reconstruction algorithm that people use for scanning. The main thing is I just need to verify which is the longest side of this surface point, and I try to connect it with my neighbors. Yeah, and usually those neighbors that is around me is those neighbors that is around a double cone, because for this cone, I can actually find a direction of my surface, and that will be actually very close to my supposed to be surface normal. And what I did is I create a cone around it, and anything that is near here, this should be the plane that I'm supposed to have the surface with. If there's a point here, I actually will connect the points to form a triangulation. That is the cone algorithm. And somehow you actually can make a pretty good surface estimation unless there's some holes. Okay, so you can see in general, if you use cone algorithm, most of the parts you actually can connect the surface. So this is actually an example, except some of the parts that with some nasty kind of geometry. But this one somehow is hard to be fixed by computer and computer alone, because computer actually have no knowledge how to do this type of area when the sampling point is not dense enough. Okay, and we need to fill all the holes, and you need some human intervention with that. Okay. One big thing is, how do you know that your triangulation actually have the same topology with your surface? Okay, so that is the question. Sorry. For scan data, you have no idea, because the scan data only will actually take in points, and the points will not give you any knowledge of what was the topology of the surface. But how about if we know it? For example, if you have an object, you want to sample some point and you actually know the object. Of course, it's a bit like reverse engineering, but what if I want to change from some functions or implicit surface, such that I want to reconstruct a triangulation that represents the surface? Let's say if my function is f, x, y, z equal to 0. For example, this is my level set or something. I can actually sample some point from a surface, right? Actually, what I do is I can, if it's really f, x, y, z is equal to 0, I can solve the equation and somehow give me some sampling points. And the next thing is I construct the Voronoi diagram. But you can actually see there are two types of Voronoi diagram. Two types of Voronoi edge. Those intersect the surface and those who don't. For example, you see the red edge actually intersect the surface, and the blue one don't. But you say, wait a minute, how do I know that if an edge is intersecting the surface or not? But you can see that an edge intersects the surface. You can simply test if the two endpoints are inside the surface or outside. And that is quite simple to teach, to test, because you can only ask if f of that point x, y, z, is it bigger than 0 or larger than 0? If both of them are like inside the surface, both of them will be bigger than 0, or both of them will be smaller than 0. For those edge that is intersecting the surface, we'll have a point inside the surface and a point outside the surface, which they actually will have a different size, different sign. And the algorithm you can do is, I only connect those points with these red edges. And these two have its broken line of the Voronoi cell that is intersecting the surface. This. And you can see that all this actually somehow reconstruct the surface. And for example, this is supposed to be in the Delaunay triangulation. This is supposed to be in the Delaunay. Broken blue edge supposed to be in the full Delaunay triangulation. You can see that they're not included in the surface, except this red edge that are approximating the surface. Okay, this method is called restricted Delaunay triangulation, which is how you reconstruct the surface with simply Voronoi and Delaunay complex. But the question is, how many sample points do I need? For example, if we sample only these 5 green points, I don't sample this white point, then you see that according to the restricted Delaunay triangulation, I got something weird. Okay, that means if you don't sample enough points, you may not be able to recover the original topology, even you know what is the surface, underlying surface. Okay, so the trick is you have to guarantee that every Voronoi cell intersecting the surface, for example, you see this yellow part, and when it intersects the surface, is actually one segment here. If you can guarantee that, it's a theorem saying that your restricted Delaunay triangulation will be the same as your surface. Otherwise, what is the thing that it will go wrong is like this. For example, you see this yellow shape actually intersect the surface in two segments. And that is where the topology go wrong. So in order to maintain this condition, usually the requirement is I sample the points in dense enough density that I actually can achieve this. Okay. So what is one sample? So the theorem set is called topological ball theorem. For each of the Voronoi cell, if it intersects the surface as a topological ball, then the restricted Delaunay triangulation will be homomorphic to the surface, which is a good thing. Okay. So a 1D topological ball is a curved segment just as this one, and a 2D topological ball is a manifold with boundary. So for example, there's a 2D surface on the left, and if you sample, it's a part of surface. If you sample the Voronoi region, and this will be the intersection of your Voronoi cell, which you can see that the Voronoi cell can be something like that. And intersect the surface is like this. And if I have guaranteed every point that intersect the surface to be like that, I will have a restricted Delaunay triangulation that will reconstruct the surface. So this is one very basic theorem that people can use to reconstruct the surface if you know the underlying surface structure. Okay, so this is one very useful thing to reconstruct the whole surface. And yep, let's see this one. So you can see that we have an underlying, this is an underlying sphere, and you can actually add points on this sphere. And all this region is actually the Voronoi diagram that is intersecting the sphere. You can see that. Okay, so when you add this, you actually will for example, this one here is actually a Voronoi cell in 3D, such that it intersects the ball to be having this. So this case, all these points actually intersect this sphere with if one region. And what you can do is you can actually see what is the restricted Delaunay triangulation, and that is the triangulation of this ball. Okay, so these are the triangulation of a Voronoi cell for this ball. Okay. So that is the first topic of today. How do you coming from a point set to a triangulation that you want? The next topic is we may not only get point set to reconstruct a surface, we may get Warsaw density. What is Warsaw density? Warsaw density means I actually have a scalar field. A scalar field in 2D, you actually can think of this as a scalar field in 2D. That means every point actually have a number. And a sampling of the scalar field is I just want a certain number, V. For example, if I just done the contour of V is equal to 1000, I actually will have a surface like that. And this actually apply to any dimension because this is the 2D map. If you have a 3D data of the data, you can actually have a 3D objects with that. We also call it isosurface or level set. So example in 2D is you actually have a function of fxy is equal to something. For example, if fxy is equal to sine cosine, if I want to, for certain values, for example, you can see all this is actually when I set this fxy is equal to a certain number k, which is all these colorful things. For example, let's say if I want to say fxy is equal to 0.4, then this pinkish yellow line is actually that surface. Okay, and for a certain value of v dash, we actually can decide which point on the grid. If we don't use because it's impossible to chase every point. So what we usually do is a visualization to simplify the data. For example, in 2D case, instead of I knowing every spot of every point of this data, I actually just sample some simple point in a grid. For example, let me see. I actually make it into a grid. So it's a bad grid, okay? I make it a grid, and I only want to know the data that is on the grid crossing. I will sample all this data on the grid. Okay. And if I have that, I have something like this. And if I want a certain value, let's say V is equal to 7, I want the level set of V equal to 7, but you can see according to my left grid, actually not V equal 7, V equal to, this is, sorry, let me change that. Oh, actually it says V equal to 5.5. Okay, sorry. So if V equal to 5.5, then you know that 3 and 5 are less than 5.5. And 8 and 6 is more than 5.5. That's why you can see that I can actually label 2 of the points, which is white, is less than 5.5. And the black point is actually more than 5.5. And if I set other values, for example, 3.5 or 7.2, you have other types of division. That means the surface should somehow go through like, sorry, I cannot share. Too bad. Sorry, wait. Let's try again, okay? So if I have a V equal to 5.5, my surface should be going through here because these 2 points here is actually less than 5.5. And this one is actually more than 5.5. And that means my surface should actually go through it. And if you set different values for V, you will have different type of surface going through it. So this is the level set of this function in which you should be constructing different values, with different V values, then you can actually get different level set. So the question is, how do we join all this? Okay. For example, if you only know the black dot and white dot, how do I can chase out this curve like that? And in 3D, it's not a square, it's actually a cube. And all the corner of the cube, for example, in this diagram, you can see the black dot over here means those dot is inside the object and the white dot is outside. Then how do I fit the surface such that it's like the right purple one? The answer is I can actually fit some surface within the cube. For example, this cube has 4 white dots and 4 black dots. Then your surface should be these 2 triangles for this cube's sake. And if you enumerate all the cases, you actually have a lot of cases that you can fit triangle to represent that division. But the problem is some cases are not trivial. For example, this one you see, if I have 2 dots that's white and 2 dots that's black, let's assume the black dots are the inside. Should your surface go like the left one or the right one? You can see that, oh, this is the inside of the objects because the 2 black dots are inside. Or you can actually say this is the inside of the object and this is the inside of the object and my surface actually have a tunnel. So which one should I have? In 3D, it's even worse. So 3D, you have, for example, you have these two dots over here. Is these 2 dots is 2 triangle like that? So such that this is the inside and this one is the inside, or is it a tube like that? So this is the inside of the object. Which one should it be? In which you have a freedom to do all of this. So the problem is you have freedom. Then the problem is how do you make the surface agree with each other for each cubes? For example, if you have a neighboring cube like this and the other neighboring, they actually neighbor to each other, you need to match the surface here, this one here, okay? And you can see that this example is showing in mismatch because this cross section is like that, and this cross section is like that, and this don't match each other. And well, you can see that what I can do is I can change the configuration because I have a few options, right? And this is actually, I don't know if you play this type of puzzle like that. I give you a puzzle, you try to put in the pieces such that each border agree with each other. And you will actually make it a real puzzle, and it's computational quite expensive. Okay, one of the solutions is do simple walking. Simple walking means I just anyhow try. Okay, of course our puzzle will not be so complicated as this because we actually do have a lot of freedom in the outside of the boundary. We shouldn't be running into that complexity. And the other one is trying to use some surface information. For example, you try to estimate the normals, the curvature, or do more sampling point. And of course, the last resort is using AI. Try to match the shape into some known shape or some example, or train it in order to make it work. Okay. So the challenge is for point cloud is how do you actually merge and stitch partial scan? Okay, so overall, because we do point set sampling, we cannot sample the whole things. And how do you stitch different partial part? And the filling holes, as we talked about in the first beginning, how do you fill holes? And point clouds always have this problem of noise because your sampling or scanning device can vibrate, can do some errors or some interference, and also repairing the geometry or topology problems, and of course, how to deal with color and texture. And for margin cubes, the main problem is our voxels, in which the voxel can be ambiguous. You have few choices to match each other. We'll actually do some exercise for both of this problem in our coming Monday tutorial that you actually can experience what is it about. Okay. And the last thing is how small is your voxel supposed to be? Okay, you actually can change the voxel size, and you can see the margin cube algorithm can actually scan different types of objects. Okay, and of course, after that, because it's margin cube, you actually have very regular pattern like that. For example, you can see the contour like that because it's margin cube algorithms, and you can see that it's not that nice. You have to remesh or redistribute the mesh to be like that, which is more nice and more eye pleasant. Okay, so that's actually the other challenges for margin cubes. Okay, so that goes our first part of the lecture about surface reconstruction, and we'll quickly go to our next topics. Unless anyone have any questions? Okay, so we go to week 6, which is our last week of lectures. So let's see what we have. We have two topics. One is procedural modeling. One is surface modeling. Okay. Let's see. Let's see some video first. Procedural modeling usually means that we actually model by some program. Okay. We talk a bit of all this. For example, one of them is grammar-based. Grammar-based, I think we learn some factors, which is plant, terrain, and other type of. I cannot cancel it. Sorry. Okay. Terrains. If you remember my 3241, we actually talk about you can actually generate factor terrains, in which you do iterations. Each of them, for example, a line that you actually raise it to be a point, and then you actually do factors. This one I will block into 2 lines, and I'll actually do this, and then somehow you actually can generate a recursive relationship. And for 3D, you actually generate 3D terrain by something like that, and you can actually have this kind of terrains. and it all generated by fractals, which is quite correct. But you can see why is it called procedural modeling is because these are more like using a program to generate it. I think now Unity or Unreal have a lot of this auto generation of terrain. And you can use it for plants also, in which you can use grammar, such that if you would change this grammar, I think this grammar is something you learn in like compiler course, and you actually have some rules. For example, I can change A to AB and B to A, and if I have that, I actually can generate a lot of grammar like that. And following the grammars, you can actually have different type of plants. I don't know if you remember this type of plant when we are using doing the 3241, the first two lectures. And all these are similar to this terrain because you can just do some grammar rules like that. And you actually can do grammar rules for buildings. Okay, the building is a bit more complicated, but you actually can set up the grammar rules of, for example, certain things you can actually spawn a window or house, and you can even do it for city scale. Sorry. Let's see. Okay. This is a game I played before. It's called Assassin's Creed. I don't know any one of you played it before. And they're actually using one of the way they do it is doing scanning. Okay, so you actually scan a real building, but the other way people do it is actually procedural modeling. Like you actually generate grammar instead of you model the whole building one by one. Which you somehow you give a basic structure, basic shapes, and you actually let the computer to generate the detail for you. For example, this is automatically generated. All these windows and things, and actually it's being generated automatically. And of course, you can actually add some of the detail by yourself. Okay, you can generate another details. And for this grammar generated, you can actually generate different buildings like that. So if you change the shape, the grammar actually will help you to change all this different shape of the windows and so on, and you don't have to model it by yourself. Okay, and then you can actually use even the procedural grammar to populate. It's a bit like your planting of your games, and all these buildings are generated by computer by some grammar rules. Okay, so and each of the building is also some grammar. So the basic thing is the whole city is being generated by some grammar rules. And even the structure of the building, you can actually change the grammar rules to different types of so-called style. So, and this is a walkthrough of the total grammar generated city. And you can even see it in a large scale like that. Okay, there's another one. So it's another style. So it's more like American style, I think. This is the Pompeii style, which is the game in Assassin's Creed. That is more like American style. This one is generating. Okay, so that's one of the technical paper about Pompeii, which is Assassin's Creed. I think it's Odyssey or no, I think it's the first Assassin's Creed that you actually model the buildings in SIGGRAPH 206 about how do you generate the building with grammar. Okay. Of course, you can generate other things like water droplet. Water droplet is, sorry, I forgot to share this. Yeah, switching is the big problem. So this is the paper of how to generate different buildings with grammar-based rule. And you also can generate a water droplet, and you, of course, you don't model each droplet by yourself. And this is distributed by your program. You can actually control the density, the size, and finally, this is the real picture you generate. Okay, for example, let's say this one. I will change the share one. Okay, this is actually the paper they're using. They actually have a video. Yeah, so first you model your object, which is maybe a fruit. And then each of the droplet is modeled by a small sphere on it. Yeah. Yeah, you could generate different droplets, and then you can blend them. And finally, yep, and it's finally how we model this water droplets on this pumpkin. Okay, so it's, yep. So maybe you can think of it as a project. You can do it for the big boss. And the other one is example-based modeling that is a bit like grammar-based, but it's not only for those structured one, in which you actually will generate like airplanes by examples. For example, this a big grammar base, right? You actually see there's a body have wings, and if you generate different grammars, you actually have different planes, like all this. So you can actually generate space station or cool objects by all grammars. Okay, so even with buildings are all, so you actually have some import models, and you actually do output models, which is more variety. This is space station based on your models, which is also the grammars, and this is a roller coaster. Okay, so you have an input model of the roller coaster, and actually you generate a very big roller coaster by your example. Okay, so there's some. That's why where's my? Okay, there's some procedural modeling example which we talk about the buildings of Assassin's Creed. This is actually trees. I didn't show this one. Yeah. So this one is. Sorry. How come? Yeah. So it's tree sketching that is using grammar base to generate trees. Yeah. You see this guy actually just draw a tree like that, and he generate a tree. Okay. Let's see again. They actually generate a tree like that. Yeah. Yeah. And you can edit the tree with different shapes. Yeah. Okay. So. Yeah. Okay. The last part is surface modeling, but let me stop this sharing and get my screen right first. Okay. Where's my screen? Okay. Hey. Oh, sorry. Okay, this is my last part of today's lecture. Talk about surfaces. Basically, we talk about a lot of surfaces. They can be divided in implicit and explicit. If you follow my 3241 graphics, implicit surface are usually a surface that is f x y z equal to 0. Examples are like metaphors, and in which you can use the margin cube algorithms to quickly generate the surface, just now as we said. Explicit surface is we actually can parameterize the surface with P, S, and T. For example, all the spatial patches and also meshes. For example, for metal balls, it's actually very simple. When you put all these metal balls, it's actually not a real ball. It's actually a ball with density. So the ball with density, you can see that it's a density function, such that the center is the most dense one, and this is like the less dense one. And if you put two balls together, because in the middle, some of the density add up, and you actually will link the ball together. So if you put all these purple dot, you actually will have this type of diagram in which the white color is different density. And you actually can put the ball with different density distribution. Some ball will be higher, some ball will be lesser. And then for this density distribution, what you can do is, I want a certain density to be my surface, or something like that. So this is like the contour of your density function. And you can just extract anyone to be your surface. In 3D, you can actually just model things, object with these metal balls, in which they actually will create density function. And you can even use a negative function to create something concave. And this is actually an example of how do you model human with these metal balls. Okay, and you can see it's quite good modeling. And this is another example of how do you model. So the implicit surface, the good thing is, it's actually quite easy to do inside outside tests, and that means it's very easy to convert it into a margin cube algorithm to become a surface model. And topological changes are easy. That means you actually can split this scorpion into two parts, and also suitable for CSG. You actually do the constructive solid geometry very easily. But the explicit surface is very easy to enumerate, which means on the surface, for example, this one, how do you draw a path from here to there? How do I traverse it? For implicit surface, it's very difficult. But for explicit surface, it's very simple because you can just walk on the surface and you can do piecewise approximation and local modification. And for implicit surface, it's hard because when you modify something here, your function may affect a very large part, and you modify something in the middle, or the side one will be actually affected. The disadvantage is it's not very easy to convert the real graphic representation by the metal ball. You see the thing is round, right? How about if I want to represent a robot? Then it's not very easy. But on the other hand, if you use meshes, if you use parametric surfaces, the problem of explicit surfaces is actually quite hard to do topology changes. And you have to really stitch and change the triangulation. Okay, and it's hard to cut and trim. You want to cut open, and you need a lot of edges if you use parametric surface. And you need to ensure continuity between patches if you're using parametric surface. And we have conversion. Let's say if I give you an implicit surface, you want to convert explicit, implicit. Implicit surface, we just explained, we can actually use margin cubes. And how about the other way? Can I express an explicit surface like a NURBS or mesh into implicit one? One thing you can do a distance function for every triangles. That means each triangle I actually do make it as a function. Any triangles to, and then I actually measure a distance to all these triangles to be the closest measure. It's very similar to margin cube, but it's in reverse way. For example, if I want to, the black lines are my objects, I actually can label the green one and the orange one as a sample point. So the green one is actually a function that is larger than the value, let's say larger than 0. And then the orange one is, let's say, less than 0. Then I use a big function fxy to fit in these points. Yeah. So, and this is actually fxyz is equal to 0. And this fxyz bigger than 0. So I just need the function to fit this whole planes in order to just make one function that actually I will do. And this summary between parametric surface and implicit surface. Just want to introduce that skin surface. That's my thesis before we end. So actually, there's a surface that I can model things. It's not that good, but you can see it's a bit like metabolls, but it's good for everything so far. It's good for triangulation, all this ray tracing, deformation, and the more, because the skin is actually made by metabolls, a bit like metabolls, but it's not metabolls. But if you decompose the skin surface like that, actually the skin surface you can see is actually a stitching of some simpler patches. So different colors are different patches, and actually there are only two types. One is sphere. So these are all sphere patches. This is actually some sphere patches, and all these are hyperbola. So even though you see the shape is so complicated, it actually consists of some sphere and hyperbola stitched together. And the good thing is you can actually deform one shape to another one. Let me show you another example of deformation. Yeah. So this is another deformation I created for my master thesis that you can actually change this to another one. Okay. And the deformation is kind of very algebraic because you can simply say that one shape is x1, the other is x2. And I can actually gradually changing one to the other like a linear combination. So I can use this t parameter to control from x1 to x3. However, the more interesting thing is I don't only limit myself to two shapes. I can actually have three shapes. So I can actually change x1 to x2, x2 to x3, and changing, you actually can change the parameter. You can actually have any path of this to go to these shapes. You have a lot of freedom to change. And you can even do negative. So this is almost like a linear combination of shapes. If you have some sources shape, let's say 1, 2, 3, 4, you can actually, within this parameter, you can actually change it to any shapes, or you can actually morph it. One of the big uses, you can do some like this caricatures effect, in which the shape is, this is the most common face on Earth. And this one is your shape. Let's say if you're Obama or that. And between this morphing, the morphing between you, your face, and the most common face on Earth. But what if you increase T, then you can be even more exaggerating your features. So there will be one shape or one type of usage of this shape morphing. In which, if you are doing your PhD or master, feel free to talk to me with more about this shape morphing. Okay, so that is the surface modeling, and that's somehow what all this course is about. Okay, we talk about quite a lot of surface model, deformations, and procedural modeling. We hope that you get something from here. And before we end, I just want to repeat what we talk about the changes of all the exams and tests. First, this is our last lecture, so we actually won't have lecture next Friday because it's a Good Friday, and NUS changes to 12 weeks of study. So week 13 is cancelled. So we have it also about, there's some material we trimmed, so but I think it's okay. This coming Monday, we still have one last tutorial, so we still be online, but we'll learn more about the restricted delonging triangulation and the margin cube algorithms. But other than that, remember that we actually will schedule a time to see your projects, how far it goes. So next week, I will actually do scheduling. So please fill in the time slot, and in which the meeting can also be online. So we just can discuss it over Zoom is good enough. And then finally, I think the final project, we also have to do it on Zoom. That means the final project presentation. I will deem it as the last day of the reading week. So after week 12 discussion, you still have 2 weeks to do your projects. Okay, so I hope everyone learned something and fun in this course. And if you have any more questions, please discuss with me after I ended the recordings. Okay, so I will end here and see you on Monday.